Hey everyone, so we're going to do a real world example for lesson 4, and it's going to involve some pieces of section 4.2, which talks about how we talk about confidence intervals, how we interpret them, and that kind of thing. And then section 4.6, which goes over the case where you have paired samples. So this is just going to be one article that was in the New York Times. So it was called Nike's Fastest Shoes May Give Runners an Even Bigger Advantage Than We Thought. So this is the article. It was published in December of 2019. And so it's about these shoes. You can see them. There's these pink shoes in the photo here. And so they did a bunch of different analyses in this article, but I'm going to focus on one specific plot that they printed. And so we can look at, how can we understand this plot? So the data that they got, it came from a fitness app called Strava. So of course, there was no such thing as doing a large scale randomized controlled trial, which means basically we couldn't do, this is not an experimental study, it's observational. So we can't make any definitive causal conclusions, but we can still construct confidence intervals and that kind of thing. So this app, the Strava app, there's a lot of runners nearly each weekend. Thousands of runners compete in races, record their performance on these watches or on smartphones. They upload the data, and a lot of them will also report what shoes they're wearing for that run. And so that's the information that they're going to be using to do these analyses. So all in all, it's results from about 5,000 or 577,000 marathons, almost 500,000 half marathons, dozens of countries, 2014 to 2019. So a bunch of data that they're looking at for a lot of different runners. And this is what the plot looks like. So on the left side here, so maybe you want to pause and take a minute to kind of take it all in, but I'll just kind of explain it briefly. So on the left side, there's a whole bunch of different types of sneakers. And then the thing that they're plotting is an estimated change in the race time compared with a previous result after switching shoes. So they have all this data, and then they have data for a specific run where the runner was wearing an old pair of shoes. So obviously it's not a specific type of shoe. It's a different pair of shoes than the one they switched to. So it's not great, but that first race is saying basically like the distribution of all shoes that runners would be wearing. They're wearing one of those. And then in the next race, they're going to be they switch to a different type of shoe. And that's the shoe that's on the y-axis here, on the left side of the plot. So the one obviously that they're focusing on is the Nike Vaporfly / Next Percent. And so that one, you've got a bunch of confidence intervals here, and that one's the pink confidence interval. And then the rest of the confidence intervals, when we say that runners have switched to all these different types of shoes, those confidence intervals are in gray. So when we interpret these confidence intervals, so you've got the top right kind of tells you how to do it. You got a best guess, and then the 95% confidence interval around that. And so you'll notice that on the top here, it has percentages, and it says slower and faster. So it's change in race time, which maybe you might think would be in like seconds or minutes. And the only thing here is they just kind of changed it so that it's in percentages. So they kind of found a way to regularize it for different runners that were really fast or runners that were really slow. It might look really different. The results might look really different. So instead of doing it in seconds, they changed it so it's in percentages. Okay. And so the one meaningful thing that we can notice right now is just that this is a paired, these are paired samples, right? Because there's two samples that we're looking at, and there's the before they switch shoes and the after they switch shoes. So one question we might have is, what population parameter are we making inference on? So we're talking about a change in race time compared with a previous result. So change in race time. And so you might get confused by the fact that it's in percentages, and you might be tempted to say it's a change in proportions, and that's not the case, because like I said, the thing where they change it to percents, like percentages, we're never going to do that in this class. This is an extension. This is something that they did in this analysis, which shouldn't be that confusing once you think about it, but it still doesn't make it a difference in proportions, right? Because difference in proportions would mean we're looking at the difference between two things that are like proportion of blank. This is not a proportion of anything. It's time. It's the measured time. So when we have time, we're always going to be talking about means. So the population parameter here is the change in means. So mu1 minus mu2, where mu1 is the mean race time after switching, and mu2 is the mean race time before switching. So it's that difference in race time. And then the sample statistic that we use to make inference on this population parameter is going to be the change in sample statistics, the change in sample means. So x1 bar minus x2 bar, meaning the mean of all of these different runners, all of their times afterwards, minus the mean of all of their times before. Okay, so you can see why it made sense for them to switch to kind of doing this kind of percent thing instead of doing seconds, because you can see how this wouldn't be as nice of an analysis if you were working on all these different scales that runners run on. So that's that. And then, so we have these confidence intervals. So that middle dot is our best guess. So we can also call that the point estimate. That's what we learned it as, point estimate. And then the distance, that distance in between the point estimate and the end of the confidence interval, we learned is called the margin of error. So here it's you're multiplying the estimated standard error times something, and that gives you your margin of error. So we can see the margin of error in the plot and the point estimate. So let's look specifically at the first one, the Nike Vaporfly shoe. So how can we interpret this? So our sentence, how we can kind of put this all together, is saying, I am 95% confident, because we know this is a 95% confidence interval. So that's what they're telling us. They constructed 95% confidence intervals. So we're 95% confident that the mean change in race time as a percentage, because that's how they're doing it in this specific case, for the population. Here the population is runners. It's basically all runners who use this app is the population that we want to infer about. After switching to the Nike Vaporfly / next percent is going to be in this interval. So we're 95% confident that that mean change is in this pink interval. So it's a pretty small interval, right? It's very small. So we could ask a question. Now we could say, is there evidence that the population parameter is different than 0? Is there evidence that the mean change, so not the change of every single runner that ever switches to the Nike Vaporfly, not like if we found a new runner and said, what's the change for this runner going to be? Not any of that. It's the change. Is there evidence that the population parameter, the mean change in race time, is different than 0? So on average, if we looked at the whole population of people who switched to this shoe, would the mean be different than 0? Would they on average get faster? So yes. Why is that? And that's because that 95% confidence interval, so we can be 95% sure that the population parameter is different than 0, because that confidence interval does not overlap 0. 0 is this vertical line right here. So you can see this is 1% slower, this is 1% faster. So this is the line where there's no change. So we're pretty sure, like, it's all the way over here, right? So we're 95% confident that it's definitely different than 0. Definitely have evidence of that. And so we could also look at a different shoe, so if we looked at the Mizuno Wave Sayonara, we can interpret this confidence interval. I'm 95% confident that the mean change in race time for the population after switching to the Mizuno Wave Sayonara is in this interval. This interval is different. This is a much wider interval. So when we ask a question again, so when we ask that question again, is there evidence that the population mean is different than 0? So is there evidence that on average, when runners make this change, that they will be faster? The answer is no. And that's because our confidence interval overlaps with the vertical line at 0. So we are 95% confident that that mean changes in this interval, and this interval includes 0. So we don't have evidence that the population mean is actually different from 0 because 0 is in our confidence interval. Okay, so that's just kind of a small part of this article. They actually did a lot of different analyses that are really interesting, and so obviously I'm linking to that that article if you're interested. But they do conclude by saying no statistical model is perfect, and because we don't have an experimental study, we have an observational study, it's possible that runners who choose to wear the Vaporfly or Next Percent shoes are somehow different from runners who do not. There's some other confounding variable that we don't know about. And regardless of the decisions that went into this model, even when trying to control for runners' propensity to wear the shoes in the first place, so they did try, they have a bunch of different analyses, like I said, so in some of them they tried to control for why runners might pick up these shoes in the first place. The outputs were similar. So they found, if you go onto that article, you'll see a lot of different evidence that they've collected that shows that this shoe makes runners faster. So here's the citation if you're interested, and I hope everyone has a good day. Thanks.